Alright, Harmony Science Academy students, AP Calculus, let's go and get into it. We're going to be looking at section 4.4, okay? Those of you guys kind of following our progression, you'll notice we're fast forwarding past 4.3, okay? Real quick, just so you understand where we're at, we have people who are getting lost a lot in notation, okay, when really conceptually I see the understanding, but I think notation involving limits, which is very important, I think having a negative impact at the moment. So we're going to fast forward. We're going to get into some mechanics, okay, see that you do understand the process, and then we can maybe go backwards, okay. So the learning topic is the first fundamental theorem of calculus, okay, which implies a second, but that's for a future video. And let's go and get into it here, okay. So what needs to be said here is, again, you guys are highly encouraged to read through 4.3, okay. It's very much related to 4.2, all right, and then of course it serves as the foundation, right, as limits do with derivatives, they do also with antiderivatives, and 4.3 will lead you nicely into 4.4, okay. And then 4.4, we've got some different things happening here, first of which is the fundamental theorem of calculus, okay. So what basically is being stated is if f of x, okay, and this is informally, but so you guys can do a visual, if your function f of x is continuous on some interval ab, okay, and f of x is the antiderivative, okay, let's see here, alright, can't access that for some reason. Okay, there's a lag here. Okay, so you've got f of x is continuous, and of course the antiderivative, or the uppercase f, is continuous, and the uppercase f of x, okay, is the antiderivative. And then there's a consequence that is to our benefit, okay, which is, right, this notation of course, this is the integration, right, the interval, right, the minimum, the maximum. Okay, so we'll be using again this theorem very much all throughout this worksheet. So when you have a problem set up like this, it's equivalent to what? Let me give you the notation first. Whoops. Okay. So again, as you guys take your own personal time to look at 4.3, get into 4.4, you're going to have to appreciate a lot of the notation. Here what we want to do is we want to get straight to the mechanics, okay? What does it say? Is when you look at these problems, okay, essentially what you're going to do is you're going to integrate, okay, little f, okay? You're going to produce large f, right, the antiderivative, and you evaluate it at b. You take that same antiderivative, evaluate it at a, and get the difference. That's it, okay? So we're not going to overcomplicate this. We're going to hopefully build some confidence and work on using that integration formula chart, okay? All right, so let's go ahead and prove it, right? Evaluate each definite integral. So pretty much that's all we're doing today is applying this theorem, okay, 1 through 24. So there is no variation besides the first the first 8 should be simpler, the next 8 intermediate, and the last 8 a little more advanced, okay? So I'll go ahead and do the first and last just to show you that this is going to take care of business for us, okay? So let's go ahead and first integrate. So what do we get here? Okay, very informally, we're going to get 2 squared over 2 plus x. And we're going to evaluate in this interval from -3 to 1. Okay? Alright, so this is going to simplify for us. Now we need to evaluate at b and then at a. Okay, so here's b. So basically we have 1 squared plus 1. Okay, and we'll just introduce another set of parentheses minus evaluating at -3 here, which is -3 squared plus -3. Okay. The reason I'm hesitating here is because we really should use the same notation as the textbook. Okay, so we'll go ahead and use brackets in that case right there. Okay, once you have it set up like this, we can go ahead and substitute, and now let's evaluate. Okay, so here we have 2. What do we have here? 9 minus 3 is 6. Okay, minus. Alright, done. Okay, we've applied the theorem, and it led us to the promised land. Okay, alright. So you guys will have different scenarios. Again, this fundamental theorem is all that you'll be using. Very valuable, as the name implies. So let's go ahead and move on to the last one. 22. It's chopped off. Let me go ahead and copy and paste it. Give me 1 second. Alright, so let's go ahead and continue here. Here's the last one. Of course, it's got to involve trigonometry, right? Popular demand. So let's go ahead and apply the theorem to this exercise here. Okay. So if you're kind of worried that this negative might get lost in the sauce, we can just kind of pull it out here for now. Okay. All right. So let's go ahead and again use this bracket notation across the board. So we've pulled out the negative, and we're going to integrate cosine, which is sine x. We're going to go from -pi6 to 0. Okay. All right. So from there, what do? You can pause the video here. Okay. So we have. I'm just going to make up this brace so that that negative applies to everything at the very end here. Okay. So we're going to have sine of 0 oops, what's it doing here? Alright, sorry for that little technical issue here. And then we're going to go ahead and have minus sine of -pi6. That's our f of a. This is our f of b. And let's go ahead and plug away. Let's see here. So again, maybe not the best use of the brace. I hope I don't regret it, but you know, I do like the symbol. So anyway, sine of 0, you guys know, is 0, right? Here we are going to have to look at the unit circle. So, right, you always revolve this way. Clockwise or counterclockwise, but starting over here, right? And the coordinates here is 1, 0. So sine of 0 here is 0. Okay. That's your cosine minus sine -pi6. Okay, so of course in radians it's always more difficult than in degrees, so you can think of this as 180, but it's negative, right? So this tells you to go positive, you go counter clockwise. Negative, you go clockwise. Okay. So here, instead of using radian, we'll go degrees. So 180 divided by 6 is 30, right? So we would create this triangle down here. Okay. And that would be your 30, 60, 90. Just a quick little review, in case you get a problem as such. Okay. And you can pause the video and kind of recall what are the dimensions. So if you said this is 1, this is 2, and this is square root of 3. Okay, that's good that you recall that. The one thing that I want to make mention of is, again, notice this why it's traveling below the x-axis, so it's actually a -1. Okay, so right when we're talking about sine is essentially what your y-coordinate over that hypotenuse. Okay, so 2. Okay, and it is a negative. I better be careful there. So I get ultimately a positive half with this negative. We're left with a negative half. Okay, I think that's good for now. We'll go ahead and deal with the rest of it in class. See you then.